Okay, today we're delving into a new area of trigonometry. Up until now, we've been dealing solely with right-angled triangles, and we're going to start to sort of build our understanding around using trigonometry outside of just right-angled triangles, and that'll sort of come over the next little while. Trigonometry does some amazing things, and what trigonometry realistically is a relationship between two changing values. You guys know sine is the opposite over the hypotenuse, and those are two distances that can change, but we don't necessarily have to put them in a right-angled triangle. There are other ways of dealing with trigonometry, and you'd have to probably start to wonder why maths teachers would spend so much time on trigonometry if all it did was help us find distances and angles in right-angled triangles. It would be a complete waste of time. But what we're trying to sort of open you up to at the moment is that trigonometry is kind of a little bit like the NASA space program in that no one expected all of the inventions that came out of the NASA space program that had nothing to do with going to space. And this is exactly what trigonometry has done. Trigonometry has created a situation where we can mathematically model many natural world phenomena, predicting earthquakes, predicting cyclones, tornadoes, dealing with many issues related to climate change, because the natural world is cyclical. It doesn't keep expanding or keep contracting always. Sometimes things happen in a cyclical fashion, and the trigonometric ratios do behave in that sort of a way. We'll get a little bit more into that in the later part of the lesson, but some of the things I just want you to make sure you understand and you've picked up along the way. The first thing is sine of a big angle is always a big result. Okay, so if we look here, this is quite a big angle in a right angle triangle up here, so this is sine beta. That's a big side over a bigger side, always over a bigger side, because the hypotenuse is the biggest side. All right. So we're going to end up with a rather large ratio. It's going to be a large ratio, but still less than 1. By comparison, sine of a small angle sorry, my writing's a bit messy, is going to be small. So, for instance, in this particular case here with theta, sine theta equals a small distance over the hypotenuse, which is quite a big distance, so that's quite small. Cos goes a little bit differently, and I think you'll pick up that if I'm talking about angle theta down here, well, while sine is quite small, the adjacent side is quite big, so cos is going to be a big distance over a bigger distance, so still a large ratio, but still less than 1. And with a big angle like here with beta, we're going to have the adjacent sides quite small over a really large hypotenuse, and we're going to end up with a really small ratio. So in all the right angle triangles, you may have picked up every single ratio you can think of sine or cos between 0 and 90 degrees is going to be somewhere between 0 and 1. And if it's sine, as the angle gets bigger, the ratio is going to get bigger. And if it's cos, as the angle gets bigger, the ratio is going to get smaller. All right, they may not be some things that you've picked up on before, but I'd like you to sort of make sure you understand that now, and you try a few numbers in your calculator to see that holds true. But in order to start thinking about non-right angle triangles, we have to think about what happens when we get to an angle bigger than 90 degrees. In order to think about that, we're just going to take an angle and put it on the Cartesian plane. The Cartesian plane is just the xy axis. So we're just going to create a line out to a point xy, which is a distance of 1 away from the origin. So I've got there a distance of 1, that's our hypotenuse. So we don't know what the x and y coordinates are because they can sort of move, but we know that in this particular case, theta is less than 90 degrees. I can't draw a less than sign. There we go. Theta is less than 90 degrees in this particular case. So what happens here, well, we'll think about it in terms of sine first. So sine theta is the opposite over the hypotenuse. Well, where's the opposite and the hypotenuse in this particular example? So our opposite's here, that's this distance here. That's our opposite. And our hypotenuse is this distance here. And we already said that we're going to make that distance away from the origin 1. And there's a reason why we did that, because when we continue along, we're going to end up with a denominator of 1. But this opposite distance is essentially our y-coordinate. That's our opposite distance right there. That's how far away from the origin in a vertical direction we have gone. So that means that sine of theta, when we make an angle theta on the Cartesian plane, is just going to equal whatever our y-coordinate is. Whatever our y-coordinate is, that's going to be sine of the angle. Likewise, if we think of cos of theta is going to be the adjacent over the hypotenuse. Now, we already know the hypotenuse is 1, and we already know where it is. And the adjacent side is going to be, just looking for a different colour highlighter, there we go. The adjacent side is down here. That's our x distance. So our x distance, whatever our x coordinate is going to be our adjacent side. So in this particular case, we're going to end up with our x coordinate over 1. So we end up with the cos of theta is just going to be our x coordinate. So we end up with our xy pairs, our xy coordinates up here effectively give us our sine and our cos ratio. Now, the reason why we've done that, it's easier to sort of start thinking about how things happen in an obtuse angle. So with an obtuse angle, and here I've got the obtuse angle theta leading up to the point, obviously it's minus x because we're on the negative side of the x-axis, of the y-axis, I suppose, but we're at negative x values, but we're still in positive y values. We're still above the x-axis. So while we're to the left of the y-axis and therefore negative for x, we're above the x-axis and therefore positive for y. So in order to describe how to get to this point, I can use that angle theta, but we don't really know how to do non-right angle trigonometry yet. We can, however, create a different triangle as long as we use the angle 180 minus theta. So if we think about this particular example, if I use the same colours as what I used before, what did I use? Yellow for the hypotenuse. The hypotenuse, we're still going with this assumption, not assumption, the rule of what we've done is that the distance away from the origin is 1. Whatever our x and y coordinates are, the distance away is 1. And we know that the opposite side, I think that's what I used here, yes, was the blue, is there. And our adjacent side to that angle is going to be down here. We'll just do a better job of doing that way. So when we think about, in this particular case, sine of 180 minus theta. Now, why have we used 180 minus theta? Because it gets us to the same position as this large obtuse angle. Right? We're talking about getting to a position. We're talking about getting to this position, xy. We want to get there. And so we can describe getting there as 180 degrees minus theta in the same way that we can describe getting there by the angle theta, where theta is a obtuse angle. So if we think about this, we're still going to have the opposite over the hypotenuse, and if we look at that angle, we're going to have a distance of y. So the opposite side is how far above the x-axis we are, which is our y-coordinate, and below the x-axis, in the bottom there is the hypotenuse, which we said was 1. So we do end up with this situation where it equals y. So just to fill in the colours so we can see where that's all happened, the hypotenuse is there, and then we used blue for the opposite side, so there it is there. And you can see that once again, our y-coordinate gives us our answer. So nothing's changed there. So let's see what's happened with cos. If we look at cos of 180 minus theta, Well, that's going to be our adjacent over our hypotenuse. So let's look at that again. The hypotenuse is there in yellow, and the adjacent side is our purple side. Okay, so what does that mean in terms of our distances? So the adjacent side, well, I'll start with the hypotenuse. The hypotenuse is 1. That was our key determiner. Some of you might like to think of that as -1, but the hypotenuse is a distance. It's how far away from the origin we have gone to get our point. So it's always a positive distance, okay? Because we've gone away from the origin. It's just a distance. It's not a coordinate, all right? But our our adjacent side is that distance between the origin back to some number smaller than the origin. So it's actually a negative x value. And if we colour that in there, so there's our negative x value, and that's where it comes out there. And obviously our hypotenuse is 1. So we end up with the situation that cos of 180 minus theta equals -x. So if we think about that and pull our calculator up, what does happen if I wanted to find, say, for instance, the sine of 150 degrees, I'm going to get 0.5. All right. But if I want to get the cosine of 150 degrees, I'm going to add a negative relationship. So we know that cos is going to be negative whenever the angle is between 90 and 180 degrees, but sine will still be positive. This creates some problems for us. Cos actually is a little bit more easygoing in this case, because we know if we've got negative numbers, then what we've got is an obtuse angle. But there's no way of knowing whether or not for every value in here, we're going to have an equal value in here. We don't know with sine whether we're getting an obtuse angle or an acute angle. We've got to actually work it out from the question. And to explain that, sine of 30 degrees is going to give me 0.5, but sine of 150 degrees is also going to give me 0.5. So if I have to key into the calculator sine to the -1 of 0.5, the calculator is going to give me the score, give me the result, which you're probably used to by now, of 30 degrees. But that also equals 150 degrees, and we have to know that an answer of a sine ratio of 0.5 could be referring to an acute angle or its pair, obtuse angle. How do I know these two are pair? Because these two angles add up to 180 degrees. And so for every value of every angle, there'll be a pair between 0 and 90 degrees. There'll be a pair between 90 and 180 degrees, where if you add those two up, they'll equal 180 degrees. And if that's the case, they'll have the exact same ratio. So we have to, when we do questions with obtuse angles, which we're going to start doing shortly, we have to start thinking about, well, what's the pair for that? And then the two, with cosine, there's still a pair, but one will be negative and one will be positive. So if I think about, for instance, let's do the same. So sine of a cos of 150 degrees is going to give us, so cos of 150 degrees is going to give us negative 0.8. I'll just go to two decimal places, I think, in this case 0.87. And cos of 30 degrees, those two add up to 180. So this should be the exact same ratio, but negative. Positive. So cos of 30 degrees gives me exactly that, 0.87, but a positive value. So for each ratio, there's a pair in first and second quadrants. Now I'm going to end the video there. There'll be a very short second video, but I just want you to sort of understand that idea. If it's a bit fuzzy, we'll work on this over the next couple of lessons.